large eruptions at Yellowstone, so much material comes out, entire mountain ranges end up falling into the ground.
Volcanoes are hundreds of thousands of years of activity. Volcanoes, and they just fucking blow, and you never know when it's gonna happen.
Yellowstone is on the brink of disaster as officials issue an urgent evacuation order due to signs of an imminent supervolcano eruption. This revelation comes after weeks of mounting seismic activity and heightened geothermal changes. But what exactly triggered this drastic measure? How severe is the threat, and what could be the catastrophic consequence? Join us as we talk about this crisis, uncovering the scientific facts and potential global impact of a Yellowstone eruption. The urgency of the evacuation order is heightened by a series of alarming events that have unfolded in recent weeks, indicating that Yellowstone's supervolcano is far from dormant. The increase in seismic activity, coupled with significant geothermal changes, has raised concerns among scientists and officials, leading to the decisive action of evacuating the area. Yellowstone has always been a hotbed of seismic activity, but recent weeks have seen a marked increase in volcanic unrest. Scientists have observed that the ground in certain areas of Yellowstone has been bulging upwards, a phenomenon known as uplift. This uplift is caused by the accumulation of magma and gases beneath the surface, exerting pressure on the crust. In the past few weeks, some areas have experienced up to 6 inches of uplift, an alarming rate that signifies the potential for an eruption. Accompanying the seismic activity are notable changes in Yellowstone's geothermal features, which include its famous geysers, hot springs, and fumaroles. Geysers that typically erupt at regular intervals have become erratic, with some increasing in frequency and intensity. For example, Steamboat Geyser, known for its sporadic and powerful eruptions, has erupted more frequently than usual, reaching heights of up to 300 feet. These changes suggest that the underground heat source is becoming more active. Hot springs, which are typically stable, have shown significant temperature increases and changes in color, indicating chemical alterations in the water. These changes are caused by the introduction of new gases and minerals from the rising magma. Fumaroles, or steam vents, have also become more vigorous, releasing greater amounts of steam and gas. These geothermal changes provide further evidence that the magma chamber beneath Yellowstone is highly active and potentially nearing a critical point. In response to these alarming signs, officials have issued a series of warnings and advisories to the public. The USGS, United States Geological Survey, and Yellowstone National Park authorities have been closely monitoring the situation using a network of seismometers, GPS stations, and thermal imaging cameras to track changes in real time. Their data indicates that the risk of an eruption has increased substantially. The decision to evacuate was not taken lightly. It followed weeks of intense monitoring and consultation with volcanologists and emergency management experts. The first official warning came when the Yellowstone Volcano Observatory, YBO, elevated the alert level from normal to advisory, indicating that the volcano was showing signs of unrest. As seismic and geothermal activities continued to escalate, the alert level was raised to watch, signaling that an eruption could be imminent. Evacuating an area as great and popular as Yellowstone is a monumental task. The park spans nearly 3,500 square miles, encompassing parts of Wyoming, Montana, and Idaho. Officials had to coordinate with multiple state and local agencies to ensure an orderly evacuation. Visitors and residents were given clear instructions to leave the area immediately, with designated evacuation routes and shelters set up to accommodate those displaced. The logistics of the evacuation involved a massive mobilization of resources. Park rangers, state troopers, and the National Guard were deployed to assist with the evacuation and ensure public safety. Roadblocks were set up to prevent unauthorized entry into the park, and helicopters were used to survey remote areas and assist in evacuating those who might be stranded. The evacuation plan also included measures to protect wildlife, with efforts to relocate animals at risk from the eruption. As people left the park, scientists continued their round-the-clock monitoring, ready to provide updates and additional warnings as necessary. The evacuation is a precautionary measure, reflecting the gravity of the potential threat posed by the supervolcano. Officials emphasize the importance of staying informed through official channels and adhering to evacuation orders to ensure safety. This unprecedented evacuation raises many questions about the nature of the threat and what might happen next. To understand why these measures are necessary and what exactly is at stake, it's crucial to get into the science behind Yellowstone's supervolcano. What makes it so dangerous, and why does its activity warrant such drastic actions? Yellowstone's supervolcano is one of the most formidable natural features on Earth, both in terms of its size and the potential impact of its eruption. Understanding what makes this volcano so significant requires a detailed look at its definition, location, historical eruptions, and the formation of its caldera. A supervolcano is a volcanic center that has had an eruption of magnitude 8 on the Volcano Explosivity Index, VEI, meaning it ejected more than 1,000 cubic kilometers, 240 cubic miles of material. These eruptions are thousands of times larger than normal volcanic eruptions and can produce massive ash clouds, lava flows, and other volcanic hazards that have widespread and catastrophic effects on the global climate and environment. The sheer volume of material expelled during such an eruption can cause long-lasting changes to the Earth's atmosphere, significantly lowering temperatures worldwide and affecting weather patterns. Yellowstone National Park, which spans parts of Wyoming, Montana, and Idaho, is home to one of the world's most studied supervolcanoes. The Yellowstone caldera, located primarily in northwestern Wyoming, is the largest volcanic system in North America. The park itself covers an area of approximately 3,500 square miles, making it a significant geographical and ecological feature in the United States. The region's geothermal activity, including famous features like Old Faithful, draws millions of visitors each year, underscoring the balance between its natural beauty and underlying danger. Yellowstone has experienced 3 major eruptions in the past 2.1 million years, each of which significantly altered the landscape and had profound environmental impacts. The Huckleberry Ridge eruption, occurring 2.1 million years ago, was the largest and most powerful of Yellowstone's eruptions. It ejected about 2,500 cubic kilometers, 600 cubic miles of volcanic material. The ash from this eruption was found across much of the western United States, and the event created the Huckleberry Ridge Tuff, a widespread geological layer that provides evidence of the eruption's magnitude. This eruption would have caused massive destruction, affecting climates and ecosystems far beyond its immediate vicinity. The Mesa Falls eruption, occurring 1.3 million years ago, was smaller than the Huckleberry Ridge event, but still significant. It produced approximately 280 cubic kilometers, 67 cubic miles of volcanic material. This eruption formed the Mesa Falls Tuff and left deposits that have been discovered as far away as the Midwest. It also contributed to the formation of the Henry's Fork caldera in present-day Idaho. The effects of this eruption, while less catastrophic than its predecessor, were still significant, altering landscapes and impacting climates regionally. The most recent major eruption, the Lava Creek eruption, occurring 631,000 years ago, ejected around 1,000 cubic kilometers, 240 cubic miles of material. This event led to the formation of the Lava Creek Tuff. The ash from this eruption spread over a huge area, with deposits found in locations across the central United States. This eruption played a crucial role in shaping the current Yellowstone caldera. The far-reaching effects of this eruption underscore the potential for future events to impact areas far beyond the immediate vicinity of Yellowstone. Now that we understand the immense power and historical significance of Yellowstone's supervolcano, it's time to discuss the science behind these phenomena. What exactly causes these super eruptions, and what clues do scientists look for to predict them? The Yellowstone supervolcano is underpinned by a massive magma chamber that drives its geothermal and volcanic activity. Understanding the science behind potential eruptions involves examining this magma chamber, the triggers that could cause an eruption, and the various scenarios that scientists consider when assessing the potential risks. Beneath Yellowstone lies one of the largest active magma chambers on Earth. This chamber is a reservoir of molten rock located between 5 to 17 kilometers, 3 to 10 miles, below the surface. It spans approximately 60 kilometers, 37 miles long, 30 kilometers, 19 miles wide, and up to 10 kilometers, 6 miles deep, containing both solid and partially molten rock. Recent studies using advanced imaging techniques, such as seismic tomography, have revealed a more detailed picture of this chamber, showing it consists of 2 interconnected reservoirs The upper reservoir is primarily composed of solid rock with pockets of molten material, while the deeper, larger reservoir contains more fully molten rock. The magma in the chamber is a mixture of molten rock, crystals, and dissolved gases. The presence of these gases, particularly water vapor, carbon dioxide, and sulfur dioxide, increases the pressure within the chamber. This pressure builds as more magma accumulates, creating conditions that could eventually lead to an eruption. Several potential triggers could cause the Yellowstone supervolcano to erupt. One of the primary triggers is seismic activity. Earthquakes are common in the Yellowstone region due to the constant movement of tectonic plates and the shifting of magma beneath the surface. These earthquakes can create fractures in the crust, providing pathways for magma to ascend towards the surface. Magma movement itself is another critical factor. As magma rises, it exerts pressure on the overlying rocks. If the pressure becomes too great, it can fracture the surrounding rock and allow magma to reach the surface. The injection of new magma into the chamber from deeper within the earth can increase the pressure and destabilize the system, potentially triggering an eruption. Scientists have developed several scenarios to understand the potential outcomes of a Yellowstone eruption, ranging from minor events to a full-scale supervolcano eruption. The least severe scenario involves hydrothermal explosions, which are relatively localized events. These explosions occur when superheated water rapidly turns to steam, causing violent eruptions of steam, water, mud, and rock. While destructive, these events are typically confined to small areas and do not have widespread impacts. A more serious scenario involves a moderate volcanic eruption. Such an eruption could devastate areas within tens of miles of the caldera, destroying infrastructure, disrupting ecosystems, and posing significant risks to human life. This type of eruption would eject over 1,000 cubic kilometers of material, covering big areas with thick layers of ash. The immediate impact would be devastating, with pyroclastic flows incinerating everything within a 100-mile radius. These scenarios, while daunting, are based on extensive research and modeling. Scientists at the Yellowstone Volcano Observatory, YVO, and other institutions continuously monitor the supervolcano using a range of tools, including seismographs, GPS stations, and satellite imagery. This monitoring helps detect changes in the magma chamber and the surrounding crust, providing critical data that can be used to predict potential eruptions and inform emergency response plans. Having explored the science behind what drives the Yellowstone supervolcano and the potential triggers for its eruption, we turn our attention to the dire consequences of these risks. The immediate impact of a Yellowstone supervolcano eruption would be catastrophic, with far-reaching consequences for both the local environment and human populations. The most immediate and visible impact of a Yellowstone eruption would be the enormous ash cloud produced. Volcanic ash, composed of tiny fragments of rock, minerals, and volcanic glass, would be ejected high into the atmosphere, darkening the sky and covering the landscape in a thick layer of ash. This ashfall would extend for hundreds to thousands of miles from the eruption site, with the heaviest deposits occurring within a 500-mile radius. Nearby states such as Wyoming, Montana, Idaho, and Colorado would experience severe ash accumulation, which could reach depths of several feet. Ashfall presents numerous hazards. Inhalation of volcanic ash can cause severe respiratory issues, particularly for those with pre-existing conditions like asthma or chronic bronchitis. The fine particles can also irritate the eyes and skin. Ash can contaminate water supplies, clog air filters in vehicles and machinery, and cause power outages by short-circuiting electrical equipment. Pyroclastic flows are another deadly aspect of a supervolcano eruption. These fast-moving currents of hot gas, ash, and volcanic rock can travel at speeds of up to 700 kilometers per hour, 450 miles per hour, and reach temperatures of about 1,000 degrees Celsius, 1,830 degrees Fahrenheit. Pyroclastic flows obliterate everything in their path, incinerating forests, buildings, and infrastructure within a 100-mile radius of the eruption. The immediate area around Yellowstone, including parts of Wyoming, Montana, and Idaho, would be the hardest hit, with entire communities likely wiped out within minutes of the eruption. Lava flows, while typically less explosive than pyroclastic flows, would still pose significant threats. The magma from Yellowstone's eruption would emerge as both fast-moving lava flows and slower-moving, more viscous domes. These flows would engulf everything in their path, destroying buildings, roads, and bridges, and altering the landscape permanently. Although lava flows move more slowly than pyroclastic flows, they are relentless and difficult to divert, causing prolonged damage as they advance. Human casualties from a Yellowstone eruption would be inevitable, particularly for those within the immediate vicinity of the eruption. The combined effects of ashfall, pyroclastic flows, and lava would result in thousands of deaths. The initial blast would be fatal for anyone within the primary impact zone, while the ensuing ashfall and pyroclastic flows would cause widespread casualties in surrounding areas. Emergency services would be overwhelmed, and evacuations would be chaotic, with limited time to escape the rapid onset of volcanic hazards. Infrastructure damage would be extensive. Buildings and homes would collapse under the weight of ash, and critical infrastructure such as hospitals, schools, and emergency response centers would be severely compromised. Transportation networks, including roads, highways, and railways, would be buried under debris, hindering rescue and relief efforts. Airports in the region would be shut down due to poor visibility and ash accumulation on runways, further complicating evacuation and aid delivery. Environmental devastation would be massive as well. The eruption would result in the immediate loss of wildlife and plant life in the affected areas, with entire ecosystems being obliterated by the pyroclastic flows and lava. Forests, rivers, and lakes would be contaminated by ash and chemicals released during the eruption. The long-term effects on the environment would include soil degradation, changes in water chemistry, and the potential for secondary hazards such as landslides and flooding due to the altered landscape. In the immediate aftermath of the eruption, the focus would shift to survival and recovery. Shelters would need to be established for the displaced population, and emergency supplies of food, water, and medical equipment would be urgently required. The economic impact would be staggering, with billions of dollars in damage and the loss of livelihoods for countless individuals. The full recovery from such an event would take years, if not decades. Rebuilding infrastructure, restoring services, and rehabilitating the environment would require extensive resources and coordination. The psychological impact on the affected populations would also be significant, with trauma and mental health issues arising from the devastation and loss. While the immediate aftermath of a Yellowstone supervolcano eruption would be dire, the broader consequences would ripple across the globe. How would such an event reshape our world? And what are the long-term implications for humanity and the global ecosystem? A Yellowstone supervolcano eruption would have far-reaching effects that would be felt worldwide. The massive ash cloud produced by the eruption would pose an immediate threat to air travel. Volcanic ash is composed of tiny abrasive particles of rock and glass that can severely damage aircraft engines and systems. When ingested by jet engines, ash can melt and then resolidify, causing engine failure. This threat was starkly demonstrated during the 2010 eruption of Eyjafjallajökull in Iceland, which led to the largest air traffic shutdown since World War II, affecting over 100,000 flights and 8 million passengers. The ash cloud from a Yellowstone eruption would be exponentially larger. The initial eruption would likely release ash high into the stratosphere, where winds would carry it across continents. Air travel would be disrupted on an unprecedented scale, starting with immediate flight cancellations across North America. The ash cloud would then spread to Europe, Asia, and beyond, potentially grounding flights for weeks or even months. The climatic effects of a Yellowstone eruption would be severe and long-lasting, potentially leading to a volcanic winter. When a supervolcano erupts, it releases large quantities of sulfur dioxide, SO2, into the atmosphere. This gas forms sulfate aerosols that reflect sunlight away from the Earth, cooling the planet's surface. Agriculture would be severely impacted, with crop yields dropping due to reduced sunlight and lower temperatures. Staple crops like wheat, rice, and corn could fail, leading to food shortages and increased prices worldwide. Livestock would also suffer from the lack of feed, exacerbating the food crisis. The ripple effects on food security would be felt globally, with poorer regions being particularly vulnerable to famine and malnutrition. By examining past volcanic events, we can gain insights into the possible outcomes and better understand the scale of the disaster we're facing. Here are some famous volcanic eruptions from the past. To grasp the potential impact of a Yellowstone supervolcano eruption, we can look at historical volcanic events such as the 1991 Mount Pinatubo eruption and the 1815 Tambora eruption. The The 1991 eruption of Mount Pinatubo in the Philippines was one of the largest volcanic eruptions of the 20th century. This event offers a useful comparison to what might happen if Yellowstone were to erupt, though on a somewhat smaller scale. Mount Pinatubo's eruption ejected approximately 10 cubic kilometers, 2.4 cubic miles, of volcanic material into the atmosphere. The ash cloud reached heights of 35 kilometers, 22 miles, spreading ash across the globe. The eruption caused a significant drop in global temperatures, estimated at about 0.5 degrees Celsius, 0.9 degrees Fahrenheit, over the following year. This cooling effect was due to the sulfur dioxide, SO2, released during the eruption, which formed sulfate aerosols in the stratosphere, reflecting sunlight away from the Earth. The initial blast and subsequent pyroclastic flows destroyed everything within a 10-mile radius. Lahar's volcanic mud flows, caused by heavy rains mixing with ash deposits, created further destruction, affecting areas up to 30 kilometers, 19 miles away. Over 200,000 homes were damaged or destroyed, and infrastructure, including roads, bridges, and power lines, was severely impacted. The eruption and its after effects led to the evacuation of more than 250,000 people, with over 800 fatalities reported. The economic impact of the Pinatubo eruption was significant. The total cost of damage and economic disruption was estimated at $700 million to $1 billion. The agricultural sector was particularly hard hit, with thousands of hectares of farmland rendered unusable due to ashfall and lahars. Another giant eruption was that of Mount Tambora in 1815 on Sumbawa Island, Indonesia. Tambora erupted with a force of 7 on the VEI, ejecting an estimated 160 cubic kilometers, 38 cubic miles, of material. The eruption column reached the stratosphere, and the ash spread around the globe. The immediate effects were catastrophic, with pyroclastic flows wiping out the island's population and ashfall, causing widespread destruction of crops and settlements. An estimated 71,000 people died, either directly from the eruption or from subsequent starvation and disease. One of the most significant consequences of the Tambora eruption was the year without a summer in 1816. The massive amount of sulfur dioxide released into the atmosphere created a global aerosol veil that significantly reduced sunlight. This led to a drop in global temperatures by as much as 3 degrees Celsius, 5.4 degrees Fahrenheit in some regions. In North America, frost and snow were reported in the summer months, devastating crops and leading to food shortages. If Yellowstone were to erupt, the effects would likely surpass those of Tambora. As we've seen from these historical comparisons, the impact of a Yellowstone eruption would be catastrophic on a global scale. But what can we do to prepare for such an event? The potential eruption of the Yellowstone supervolcano demands preparedness and response strategies due to the possible catastrophic consequences. Government agencies and the scientific community have implemented robust monitoring systems, developed comprehensive evacuation plans, and continuously work to educate the public on safety measures to mitigate these risks. One of the primary tools used is a network of seismographs strategically placed around Yellowstone. These instruments measure and record seismic activity, providing critical data on the frequency, magnitude, and location of earthquakes. Increased seismic activity often indicates magma movement beneath the surface, a crucial factor in predicting potential eruptions. In addition to seismographs and GPS stations, the USGS employs satellite imagery and remote sensing technologies. These tools allow scientists to observe changes in thermal activity, surface deformation, and gas emissions from a broader perspective. Thermal imaging can detect increases in heat from geothermal features, while gas sensors measure levels of volcanic gases like sulfur dioxide, SO2, which can indicate rising magma. Effective evacuation plans are a must in the event of an impending eruption. The USGS and emergency management agencies, including the Federal Emergency Management Agency, FEMA, have developed detailed strategies to protect the public. The primary goal is to evacuate residents and visitors from the most dangerous zones closest to the caldera, where pyroclastic flows, ashfall, and lava would be most devastating. Emergency response teams, including firefighters, police officers, medical personnel, and the National Guard, are trained and ready to be deployed at a moment's notice. Their roles range from directing traffic and ensuring safe passage out of danger zones to providing medical care and support at evacuation centers. Regular drills and simulations are conducted to keep these teams prepared for a real-world scenario. The use of technology is integral to modern evacuation plans. Alert systems, such as the Integrated Public Alert and Warning System, IPAWS, are designed to disseminate emergency messages quickly through multiple channels, including television, radio, mobile phones, and social media. This ensures that the public receives timely and accurate information on evacuation orders and safety instruction. One of the key messages emphasized is the importance of staying informed. Residents and visitors are encouraged to follow official sources for the latest updates on volcanic activity and potential hazards. Signing up for emergency alerts and knowing the evacuation routes and safe zones in advance can make a significant difference in an emergency. Safety tips for the public include having an emergency kit ready that includes essentials like water, food, medications, a flashlight, batteries, and important documents. Each family member should know the evacuation plan and meeting points. During an eruption, if indoors, it's crucial to stay inside to avoid ashfall and falling debris, closing windows and doors to prevent ash from entering. If outdoors, seek shelter immediately and use masks or cloths to cover your mouth and nose to prevent inhaling ash. After an eruption, remain indoors until authorities declare it safe to go outside, avoid driving unless absolutely necessary, and follow official updates on road conditions and when it is safe to return home.